Hello guys, welcome to the second part of the lesson for today, Earth and Beyond. In this lesson, we're going to be looking at the moon, satellites, that is artificial satellites, eclipse, and then we'll proceed to geocentric and heliocentric model of the Earth. Okay, now let's quickly start with the moon. Now, if you look at the picture there on your screen, you're going to see several stages of the moon. Okay, or several phases of the moon, as the case may be. The first phase here, where it's totally covered with a shadow, is called the new moon. At this stage, you don't get to see the moon, right? Because it's totally covered. It's directly in front of the sunlight, so it's totally covered. So there's no way you can get a reflection of the moon, reflection of light coming from the sun by the moon. So it's totally covered, right? Now, this is the second stage. Now, if you look at this stage, you notice that we have a crescent pattern here, like a banana-shaped pattern here. Okay, that this side is actually the bright side that you see, and the other side is the side that is hidden. Okay, because of the shadow that is cast on it. Okay, now this is the part that is actually reflecting light to the earth. Wherever you are in the earth here, you can see this, because that is the part that is reflecting the ray from sunlight to you. Okay, it's called the crescent waxing moon phase. Okay, now I want you to notice something. Notice that in all of this case, the shadows are by the left hand side. The shadows are by the left hand side. We'll have 1, 2, 3 cases here, but we'll have our shadow by the left hand side. This is a shadow, it's a shadow. Okay, that means whenever you go out and you see you look at the moon, and you observe that the side that is bright is the right one, the one on your right, you should know that you are in the first half, okay, phase of the moon, or you can call it the waxing stage of the moon, okay, where it's coming up. So this is the waxing crescent. This stage is a half moon, where only half of it reflect light from the sun, but the other half is hidden from view. Okay, like you can see here. So it's called a half, or you can call it the first quarter or a half moon. This one here is a gibbous waxing. And if you look closely, you see the shadow somewhere here. Okay, most part of the edges are bright, except for this little part here. It's covered with shadow. Okay, so that's a gibbous moon. And then you move down to the full moon. At this stage, all of the surface, the side that is facing the earth, is reflecting the rays coming from the sun. Okay, to whoever it's observing, the observer here. Right, now from this one, it will return back to the gibbous, but this time around, it's going to be a waning gibbous. It's phasing out. Now notice that the shadow now is on the right hand side. So the position of the shadow determines if it's going to be waxing or waning. All right, it's going to be waning, it's going to be waxing. This is the half moon, the last quarter of it. And then it's a crescent, waning crescent, and then back to the new moon. So the stage is the process. Stage continue on and on for 29 days, like that. Okay. Now let's see from this animated view of what's actually happening. So this is the first one we saw, the new moon, and as you can see, the sunlight is coming from this side, and there is no part that is reflecting the sunlight directly in front of the ray. So we get to see it totally dark. Okay, because it's not facing the ray. The side that is facing the ray, which is this side, is bright, as you can see it. Now this is the second stage, the crescent moon. But remember, we said in this stage it's called waxing because coming up. Okay, it's actually increasing in size. The bright side is actually increasing. So that's a waxing crescent moon. The half moon, the gibbous, waxing gibbous, then the full moon, where all of the face or the side, all of the moon surface facing the sun directly is reflecting light to the earth. Okay, and then we go to the waning stage where we have the gibbous, the half moon, the crescent, waning, and then back to the new moon. Like I said, notice the direction of the arrow, the direction of the shadow, sorry, the position of the shadow. Here it's to the right when it's waning up. Here it's to the left when it is waxing. Okay. Now, can we complete this? What does the moon look like from Earth in each of the position? Let's see how we can do that. So this is the new moon. Drag it to the side. Good. The second one. Notice that the shadow is to the right here. Okay. So when it's waxing, the shadow is always to the left. So since the shadow is to the right here, it's a crescent moon. I have to take it to the waning crescent. This is the waxing crescent. Shadow is to the left-hand side. This is a half moon last quarter. It's a gibbous, shadow to the left-hand side. Half moon, first quarter. The new moon, that's full moon, sorry. Then the gibbous, waning gibbous. Okay. Hope we are okay with the different stages of the moon. Okay, let's move ahead. Now, this side, if you look at this diagram, we have a red dot here showing the far side of the moon. You don't get to see the far side. That is the other end of the moon. You only see one side of the moon because the moon rotates about its axis as it orbits the Earth. It happens to take exactly the same time to rotate about its axis as it orbits the Earth. Okay, now for this reason, you don't get to see this. As it's moving like this and moving like this at the same time, at the same speed. Okay, so we don't get to see the other side. The other side that we cannot see with the red dot is called the far side or the dark side. So for you to see the dark side, you need to either take a picture from space, maybe the Hubble Space Telescope can help in that case. Okay, there's any way you can get a picture of the other side that you don't get to see from space, then you'll be able to see the picture. All right. So like I said, the reason is because the rotation about the axis of the moon and the revolution about the Earth, about its orbit around the Earth, is at the same speed. So that's why we see only one side of the moon. All right, let's move ahead. Tides. Now, moon actually, it's the major cause, or it's the cause of tide. I would say the major cause because it's the only object that is quite closer to the Earth and exerts its gravitational influence on the Earth. Okay, so the rising and falling of water level or ocean is actually what is called tide. The moon and the sun gravity makes water bulge out of the Earth, but the moon has more influence than the sun because the sun is way far from the Earth. Okay, the moon gravity has a greater effect because it's closer than the sun. The area aligned with the moon is a high tide. And look at it. The moon is actually pulling water towards itself. Okay, cannot pull the land, so it pulls what it can actually pull. So it's pulling water towards itself. Remember, the Earth's also exerting gravitational pull on the moon, which makes it to move round and round the Earth. Okay, at the same time, the moon is exerting its own pull on what? On the Earth or on oceans, water. All right, so here we have our high tide, on the other side we have our low tide. Let's quickly go back. That's a spring tide. Now the area aligned with the moon is a high tide, and the area not aligned with the moon is the low tide. Now this side is the neap tide, okay, when the moon is on this side, the third quarter. But this is when the moon is on this side. Okay, now let's quickly complete this. Complete the sentences about the moon. The moon causes tide because it pulls Earth dash towards it. So let's see, Earth water towards it. There is no dash on the moon because of low gravity and lack of volcano. You know, volcano release a lot of ash and dust and gases. So there's no volcanic eruption in the moon. So for that reason, we don't have an atmosphere there. There's no atmosphere because of low gravity, okay, and lack of volcano. Whatever is there, whatever gas you take there will not be able to be held in place because of low gravity, right? We need an attraction, something to attract to keep it in place. There is evidence that the moon, well, we have to go up. I think some areas are missing. Okay, let's move up. The moon does not produce its own light. It reflects the sun's light. The moon takes around days to orbit the Earth, roughly 27 days. Okay, so in some cases, it's 29 days, but this is just a rough, okay, the case, an approximate case. A new moon is when dash of the sun light is reflected off the moon towards us, when none of the sunlight. So for no new moon, no light ray is being reflected. Dash keeps the moon in its orbit around the Earth, gravity. Then there is evidence that the moon was thrown out from dash during a huge collision millions of years ago. There's an evidence that it actually was thrown out of the Earth during a planetary collision, a planet hitting another planet, okay, millions of years ago. Let's proceed. Solar eclipse. How does it occur? When does it occur? And why does it occur? A solar eclipse happens when the moon passes between the sun and the Earth, okay, casting a shadow over the Earth. So if there's any case where the moon happened to pass, like what we have here, like the moon here, the sun here, the moon is actually trying to pass, that's when it occurs. So whenever we have the moon perfectly in a straight line between the sun and the Earth, we will have our solar eclipse. The lunar eclipse, or you can also call it the eclipse of the moon, happens when the Earth passes between the sun and the moon, casting a shadow over the moon. All right, so in this case, the Earth now is moving, passing between the moon and the sun, casting its shadow or preventing light from reaching the moon. Right, that's when we have our eclipse of the moon. Lunar eclipse happen in most of the years. Where must the moon be for a solar eclipse to take place? Okay, this diagram perfectly explains where the moon must be. The moon should be able to be between this and this, okay, for it to occur. During a solar eclipse, the moon moves directly towards the sun and the earth, blocking the sun rays from reaching part of the earth. The part with the deep shadow is called the umbra. It's a total eclipse. The part with the light shadow is called the penumbra, the partial eclipse. So when the moon is between the shadow here, we have a part where we have total darkness. We'll have a part where we have some light reaching, a little amount of light getting to it, getting to that part. That part, we call it the region that experiences partial eclipse, or the penumbra region. Okay, the umbra region is the area, the region that is actually being blocked, that are blocked, totally blocked by the shadow of the moon. All right? Where must the moon be for a lunar eclipse to take place? Now, um, let me repeat myself. Where must the moon be for lunar eclipse to take place? Can you see the position of the moon here? So the moon must be behind the earth for this kind of eclipse to take place. Okay, so here we have the moon behind the earth. So the earth is between the sun and the moon. So the shadow of the earth here is actually cast on this, making it to look totally dark. Okay. During a lunar eclipse, the moon is on the opposite side of the earth to the sun, blocking the sunlight from reaching the moon. Now, these are the pictures of animated picture of how it looked like when you observe it from space. Can you see the shadow here? The shadow. This shadow here on the earth is actually this shadow here, the thick one. It's actually the one that causes the total eclipse on specific point on the earth, which we call the umbra shadow. While this one that is not too dark is a penumbra shadow, the one that creates the partial eclipse on this region. Okay, now this picture is just for the solar eclipse. Now, look at this one too. What did you observe? What did you observe? This is the earth. This is the moon. Notice that the earth here is obstructing, totally obstructing the moon. Right, so for somebody on the surface of the moon to observe this kind of the changes taking place. The earth obstructing light from reaching the moon, causing a total blackout. Why don't we have eclipse often? So if eclipse is all about obstruction of one planetary object by another, why doesn't it frequent itself? Okay, like the solar eclipse, why don't we normally see it often and on? Why is it rare? That's the question. Now, they do not happen often every month because the Earth orbits around the Sun. The orbit is not the same in the same plane. Okay, now the orbit of the Earth is this way. Let me use this. The orbit of the Earth, if the Sun is in that direction, is this way. This is the plane of the orbit. Okay. Okay, this is the plane of the orbit of the Earth. And can you see the plane of the orbit of the moon? Slightly at 5 degrees to the horizontal. The moon, as if it's bent, tilted. The orbit itself tilted at 5 degrees to the horizontal. Can you observe it? So for this reason, there is no way it will hardly, there will be, it will, for this and the sun to align, to be in a straight line, will hardly come to be. What I mean is, we hardly see a case or rarely see a case where the moon, the Earth here, and the sun somewhere there will come to a straight line. It doesn't mean it doesn't occur to occur, but it's not going to be frequent. Okay, maybe when the moon gets to the side. Okay, that's the reason why it's not frequent. The moon orbit is slightly tilted and is constantly changing. So for eclipse to occur, the moon, the earth, and the sun must be in the same straight line, which rarely occur. If the moon orbit is not tilted, then the earth will block out the light from the sun, and we will not see the full moon, since no light can reach the moon from the sun. Now, this is a consequence if it is not tilted. Let's assume it's not tilted and this is the moon. The moment this moon gets to this line here, what will happen? The shadow of the earth will totally be cast on this moon. So we won't be able to see the full moon. The full moon has to be somewhere here for you to see. If this is the sun, if I have the sun here, if I have the sun this point somewhere here, that's the sun, and I have a moon here. I have my moon somewhere here. Now you observe that the shadow, it's on the shadow, right? But if I have my moon somewhere here, an observer here will be able to see the moon. All right, so the rays from this sun here can actually get to the moon here, right? And the observer here can see it. So if we have a case, let's say that the orbit is not tilted, this is a case we happen often. You won't be able to observe the full moon. Okay, but because the orbit is slightly tilted, we can observe the full moon because rays from the sun, which is the moon itself, and it's reflected to the earth. Now let's go through this quickly. What are the missing words about eclipse? Eclipse lasts just for a few minutes. Yeah, lasts just for a few minutes because the moon and the earth are constantly moving, right? So we don't expect it to last all day. It lasts just for a few minutes. Solar eclipse occur when the moon comes between the sun and the earth. Lunar eclipse occur when the earth comes between the sun and the moon. During an eclipse, the sun and the moon appear to be about the same size. Yeah, when you look at it, when you view it from Earth, it appears to be the same size. This is because it's actually because the sun is 400 times much more bigger than further away from the moon. Okay, and the diameter is 400 times much more larger than the diameter of the moon. Okay, so during the eclipse, the sun and the moon appear to be about the same size because the sun is 400 times further away from us than the moon, and 400 times larger in diameter than the moon. So eclipses are rare in any particular place, but are seen from somewhere in the earth about every 18. So there are regions that actually that this eclipse frequent, mostly at the poles. Okay. where we have uh, frequent kind of obstruction of the moon, obstructing light reaching the Earth. There are regions like that in the Earth, but the region is just secluded regions. Like I said, regions at the poles. Satellites, gravity and sunlight. Now, because that I told you the moon is a natural satellite of the Earth. The moon is a natural satellite because it actually orbits the Earth. A satellite is an object or a body that orbits another object. Okay, we have several artificial satellites in space. A lot of artificial satellites, but we can categorize them into two groups. Okay, based on their movement, how they move. Right. So an artificial satellite is an object made by and put in place by humans. Why do you think satellites stay in orbit instead of falling back into Earth? They're actually being held by gravity. They're falling. Yes, they're falling. They're being attracted, but they're falling at a very fast speed. So they keep falling, they keep going up around the object. Okay, they keep falling towards the object. Okay, in each case. Right, that's the gravity, that's the orbiting we're talking about. Now, we can categorize them into two groups. But before we do that, let's quickly go through this. A satellite is anything that's something else that orbits something else. It goes around something else. The Earth has a natural satellite. This is the moon. The Earth is also a satellite as it orbits the sun because it's going around the sun. So it's a satellite of the sun. The Earth has hundreds of other satellites orbiting around it. All satellites need two things in order to stay in the orbit. One, they need to be moving very fast, and they need a force of gravity. If you're not moving very fast, what happens? You fall towards the Earth. You need to be moving very fast, and you need to be attracted, the force of gravity, to keep the movement in place around orbit. Okay. Like I said, all satellites can be categorized into two: the geostationary, based on their orbit, how they move, and the polar orbit satellites. Okay, for the geostationary, this is an example of a geostationary satellite. Now, notice that it's in a single point, stays in one point, fixed, rotating at the same speed as the Earth. Okay, that means it takes a geostationary satellite 24 hours to move around the Earth. It's always on a fixed point. You always see it to move around to complete an orbit. All right. So the other one is a polar satellite. These ones are much more faster and lower and travel around the poles. Now notice that it's going around, and it's notice the red lights there on the satellite. Get it? You've noticed it. See if it's trying to gather information, facts from some certain regions. Okay, these ones are called polar satellites. They can be used for spying, to gather intelligence in regions. They can be used for large-scale weather forecast, maybe global kind of weather forecast, and some other things. Okay, the previous one can be used for television, TV transmission, weather forecast within a region, maybe in a country, for the monitor weather condition, all of that. Oh, this has been solved already. Okay, let me just put it back in place. Geostationary. Does each statement apply to geostationary polar satellite? Used for communication. Satellite TV, weather, forecast, GPS. In geostationary, they're the ones used for communication, TV, satellite TVs, and weather forecast. Speed of orbit is not the same as the Earth rotation. That's polar. stays above the same point on the Earth, that you're stationary from what we saw. Used for large-scale mapping and global weather monitoring. That's polar. Speed of orbit matches Earth rotation, that's geostationary. And low orbit, that's low orbit, passing over the north and south poles. That is south. Good. Solar system and the universe. Basically, everything in the universe orbits around something else. Earlier in the part of this video, I told you that even though our sun appeared to be still, and for explanation, for understanding sake, we assume it to be still while other planets are going around it. The sun also moves to a certain degree. Okay, our sun is one of the millions of stars that orbit the center here. So we have a lot of stars orbiting this. You can see a spiral kind of display here. It's a galaxy, Milky Way galaxy. So our sun is part of it, one of it, maybe somewhere towards the edge of it that is orbiting the center here. Okay, so the Milky Way, which is one of the billion galaxies that orbit and move away from the center. So the Milky Way also is moving. So everything actually has a degree of movement. Okay, that is when we are conveyed to have a relative motion with respect to another. All right. A galaxy, a galaxy actually is a system of millions or billions of stars together with gas and dust held by the gravitational attraction, usually at the center. You can see this is an example of a galaxy. Okay, orbiting, also held by a stronger, very strong gravitational attraction somewhere in the middle. It is believed that somewhere here we have a black hole. Maybe that's a lesson for another time. Our galaxy, the Milky Way, is typical. It has hundreds or billions of stars, enough gas and dust to make billion more stars. And at least 10 times as much dark matter as all the stars and gas put together, so many black matters. And it's all held together by gravity from the center, right? Like more than 2/3 of the unknown galaxies, the Milky Way has a spiral shape. This kind of spiral shape. At the center of the spiral, a lot of energy and occasionally a vivid flare often occur, are being generated based on the immense gravity that will be required. Okay, based on this gravity, the explanation and the movement, which explains the movement of stars and energy expelled, astronomer concludes that the center of the Milky Way is actually a supermassive black hole. Okay, that's for another lesson, black hole. But it's believed that the middle of our galaxy is actually a black hole, right? Remember how a black hole is formed. Now we go to the geocentric model. Years back, people believe that the Earth, I'm talking of hundreds of years back, people believe that the Earth is the center of the universe. It was a common belief there. Okay. Now, based on this belief, these astronomers, these popular astronomers, Plato and Aristotle, they actually propounded and came up with this model or this theory. Okay. They actually believe that the Earth was the center of the universe, and every other thing revolves around the Earth, moves around the Earth. But there was a big gap in what they believed and in their model, and that gap was they couldn't explain why some planets appear to move backward and forward. That is wonder about in the sky when you observe it. Okay, so they couldn't explain what we call today the retrograde motion of planets. They couldn't explain that. So there was a serious loophole there. Okay, now let's quickly take just 3 minutes to watch and see how the model of geocentric model look like. How a geocentric model look like. In the model here is the Earth. At the center, these are stars round about 8, forming what we call something like a sphere. Roundabout. Can you see it? And the Earth is like a driving force, controlling every other thing. That is, every other thing revolves around the Earth. Like you can see the stars there around the Earth. This is an idea of how a planet moves. In a geocentric model. Now, if you notice, look closely, you notice that this planet keep going backward and forward as it moves around the Earth. This is the orbit. It's actually following its orbit. And the orbit is constantly changing. The plane is constantly changing. But at the same time, it's going back and forth, like that. You see it. Now, this is an idea of how a geocentric model look like. This is what the idea they had in those days. They believe that all objects in space move on sphere around the Earth. The Greek astronomer thought that there were 7 planets: the Mercury, Venus, Mars, Jupiter, Saturn, the Sun, and the Moon, and even the Sun inclusive. They thought the Sun was a planet. They also believe that the center of the universe was the Earth because the Earth does not feel as if it's moving when you're standing. Like when you're standing now, wherever you're standing, it appears as if it's not moving. So that gives them that that belief that the Earth must be the center. And if you drop something, it always falls towards the center of the Earth. That's another belief, another popular belief. Why is it that whenever you drop something from anywhere, it always comes to the Earth? It means the Earth is the center. Okay, so that was their argument in those days, right? But like I said, there was a flaw in their theory, in their model. There was a flaw. They couldn't explain why planets had to go back and forth. Okay, so to explain this flaw, another astronomer, Ptolemy, came up with this model. That's an improved model, an improved version. Okay, he added smaller cycles to the already existing orbits. These smaller cycles, he called them the epicycles. Ptolemy model assumed Earth's orbit round, assumed planets orbit around the Earth in circles and also travel in smaller circles called epicycles. Like this, look at this. This will show you a good picture. So that's why planets appear to be going back and forth. And they also travel around smaller cycles, even though they are going around this, they're also going around smaller cycles. That's why they happen to go back and forth when you observe them from the Earth. The model actually gained popularity in those days because it explains the motion of the stars and planets. It was able to explain it those days. And it also predicted their future position. It can predict the position of the planet the position of the stars, okay, in those days. But after a few years, in 1500, Copernicus published a different idea, okay? He called this idea the heliocentric model theory. He stated that the sun is actually the center of the universe, it's fixed. Gravity arises from the center of the earth, okay? And the movement of the stars is actually the rotation of the earth. So this is very close to what we believe today, right? Except for this sun is the center of the universe. So he came up with this model, as you can see, the model of the solar system, the sun. We got a model of the solar system from Copernicus theory, the sun, other planets moving around, okay? But there was still something that needed to be explained, the retrograde motion. So he goes ahead to explain the retrograde motion, and it was so smooth and clear. Okay, I said if this is the position of the Earth is going round, and this is Mars, for instance, the orbit of the Mars, it's the orbit of the Earth. And the Earth is here, and the Mars is ahead. An observer in the Earth will see the Mars ahead, at the front. It's like you're driving a car, you are in the top speed, and you happen to, you see a car ahead of you, and you're in a top speed. You want to overtake the car, but the car is ahead of you, okay? And then at position 2, you will also see the sun ahead. It's also see the Mars ahead. Position 3, also see the Mars ahead. But at position 4, when they're almost at the same straight line, he will observe the Mars behind. Okay, it's like you're overtaking the car, as if the car is going backward, right? If you're in the top speed and you're overtaking a slow-moving car, it will appear as if the car is moving backward. So that's exactly what he was saying here. And if you're ahead of, here the Earth's ahead of Mars, you see Mars now behind, falling backward behind you. Okay, now at 6, ahead of Mars, and you see Mars as if it's, the speed is coming up, as if it's coming up, still behind you, but as if not the way it was before. Okay, so that goes on and on, right? So with this explanation, people, come to accept this heliocentric model because the explanation was so simple, was not complicated, so smooth. Now, another guy that worked on to support Copernicus' view is Galileo. An Italian born in 1600, was an astronomer, a physicist, mathematician, and a philosopher. He actually supported Copernicus. He used improved telescope to observe the location of heavenly bodies and was able to observe Jupiter's moon. Okay, so from Jupiter's moon, he came up with something that since we have moon orbiting other planets, so it's not possible for everything to be orbiting the Earth. Now, another guy that supported that idea, Johannes Kepler, worked and improved on Copernicus' idea. He's a German and was born in 1600s. It's follower of heliocentric theory. He described that the planet move in elliptical orbits, not in circles. Okay, make little adjustments to Copernicus theory. Now, the next one is Isaac Newton. He's an Englishman, born in the late 1600s. He united experimentation and theoretical maths, created a lot of mathematical laws that explain motion. We know him as the motion guy. He propounded several laws, including the famous gravity, experiment on gravity. Okay, so he actually discovered that gravity is what causes object to fall. So that disproves the previous idea of the geocentric model. Gravity is actually what causes every object to fall towards the center of the Earth. Then we have Hershey and Galley that discovered Uranus, that is an ice giant, and the other one, Neptune. Okay, now let's quickly go through this. Now, how have ideas about the solar system changed? Let's look at Ptolemy's idea. Can you see Ptolemy's idea clearly there? While planets are going around the sun, they're also going around themselves in epicycles. Okay, he added this cycle just to explain the back and forth movement, the retrograde motion of planets. Can you see? Except for the sun. And this is the modern idea now. This is our modern idea. Our modern idea was actually derived from Copernicus theories and improvements on Copernicus theory. Can you see the sun? The sun is at the middle with all planets going around orbiting. Okay, a quick one. Let's omit that. You will be a start in this quiz. Okay, this is just a little exercise that we need to do, and then back. Now, this exercise, I think I'm not going to take much of our time. We already wasted a lot of time. So with this, I believe for your checkpoint exams, Earth and Beyond will be very smooth. These are the essential things you need to know. Please, if there's any other thing you need to know, please comment below, like my video, and subscribe for more of this. Thank you.